Okay, the next thing that we want to talk about, continuing on where we left off, is how the difference between energy levels between, say, 4 and 5 or 2 and 3 or 2 and 5 is not the same for each transition. So just by way of example, let's sort of run through a light version of calculating the energy of particular levels. So energy of, let's say, n equals 2. So that's the same thing as negative RH over 2 squared, or negative RH times 0.25. Right? So if I go to n equals 3, negative RH over 3 squared, negative RH times 0.11. The difference between those two energy levels is 0.14. Now if I go to n equals 4, that's RH times 0.0625. The difference between those two energy levels is less. If I go to n equals 5, the difference between those two energies is less still. Okay, so the point being is that as the n value goes up, the distance between the energy levels gets smaller. So if I'm looking at a scale, energy being higher at the top, so let's say here is n equals 2, let's say here is n equals 3, then n equals 4 is somewhere around there, and then 5, and then 6, and then 7, and so as the n value goes up, the difference between energy levels gets smaller. Okay, so a transition from 2 to 3 is associated with a larger energy than the transition for between 3 and 4. Okay, so far we've only done practice problems involving transitions from higher energy level to lower energy level, and those are emission transitions. But we can also talk about energy transitions from going from low to high. So let's change colors, and let's say, what is the delta E for transition from n equals 2 to n equals 4? Okay, going from a lower energy level to a higher energy level means that I have to put energy in. So we have our equation for calculating a transition, a change in energy. So that would be 1 over 2 squared minus 1 over 4 squared. Okay, so notice this energy is positive. So delta E is positive. So it gains energy. Right, so this would be an example of excitation or absorption. Okay, so that Bohr atom has to gain that much energy in order to move an electron from the n equals 2 level to the n equals 4 level. Okay, so going to step away from this particular topic in order to sort of give some background in order to talk about larger atoms. Because all of this work is about a Bohr atom, which is a single electron species. Right? But the Bohr model doesn't work terribly well for larger atoms or larger things. Okay, so in order to talk about larger atoms, multi-electron atoms, we get into the beginnings of quantum theory. Okay, and the two main ideas of quantum theory, first is the idea of wave-particle duality. Okay, that everything has wave characteristics and particle characteristics, all right? It's a dual behavior. And the second main idea is the uncertainty principle. Okay, so to address that first idea is that everything, every object has wave-like behavior. Okay? The important aspect of that is that the smaller the particle or object, the more significant the wave-like behavior is. Okay, so in order to do this, to talk about this, we have the de Broglie wavelength equation. Okay, and that equation is given to us by lambda equals h over m times n. All right, so this is Planck's constant. Okay, and we take the units for Planck's constant are joules seconds, but we're going to put joules in terms of the SI units. So the units for Planck's constant here will be kilograms meters squared over seconds squared times seconds. Okay, so the kilograms meters squared second squared, that is a joule. So joules times seconds, which means that our mass is in kilograms. Okay? And I'm sorry, that's not m times n. That should be m times velocity. My bad. And the velocity will be in meters per second. All right, so let's do a couple of examples and see how things are different depending on their size. Okay, so let's take a large object, a macro-sized object, something that I can pick up and carry across the room. So, large object traveling at 2 meters a second. And has a mass of 76 kilograms. Right, so the wavelength of that macro-sized object, Planck's constant, 6.626 times 10 to the minus 34 kilograms meters squared over seconds squared times seconds. We have mass, 76 kilograms, times the velocity, 2 meters per second. We convert that to nanometers. And we're going to find that that wavelength of that macro-sized object 4 times 10 to the minus 27 nanometers. Okay, so completely insignificant. Okay, that wavelength is so incomprehensibly small that it has no real bearing on physical reality, okay, for a large object. But let's say instead we look at it for an electron. Traveling at 0.1 of the speed of light. Okay, so 1/10 of the speed of light. So not even traveling at the speed of light. Right, so only 1/10 of that speed. Our de Broglie wavelength for an electron traveling at that speed so the mass of an electron in kilograms is 9.109 times 10 to the minus 31. And the speed of light, 1/10 of the speed of light, 0.3 times 10 to the 8 meters per second. Okay, that gives us a de Broglie wavelength for the electron, 0.0242 nanometers. Right? Those are X-rays, which are completely practical. Right? So the smaller the object, the more significant the wave-like behavior is. So a macro object, something the size of a human being, the wavelength is so small that it's completely insignificant. All right? But when I get down to tiny objects, electrons, protons, photons, whatever, subatomic particles, now the wave-like behavior actually becomes important. Okay, so I'm going to go ahead and stop this video right here, and we'll pick it up on the next video talking about the uncertainty.